All right, today we actually start chapter 4. This is kind of another big change in what we're doing, but I think 4.1 is just a beautiful section in that it's a perfect bridge between chapter 3 and chapter 4. What we'll be doing in chapter 4 is solving systems of equations. So back in chapter 2, we just had one equation with one variable. Now in chapter 4, we'll have two equations and two variables. And when you get onto Math 1010, you'll have three equations and three variables and four equations and four variables. But the methods you'll use in 1010 are exactly the same as the methods you will learn right now. The problems will just be a little bit harder. So we will do three different ways of doing exactly the same thing. The first way that we'll do it is we're going to solve a system of equations by graphing. That's 4.1. And then we will solve a system of equations by substitution. That is 4.2. And then in lecture 14, we will solve a system of equations with elimination. The reason I like chapter 4 or section 4.1 so much is not only is it a bridge between graphing and systems of equations, it really, better than anything else, illustrates what's going on behind the scenes. So that even if you're in the middle of doing it with substitution or elimination, you can visualize what's happening with your solution. So let's start with 4.1. Okay, now remember, when we very first started graphing at the beginning of chapter 3, we talked about what the graph of y equals 2x minus 1 really means. You've probably forgotten what it means. That's okay. You've been so focused on how to graph it, you forgot what you were actually graphing perhaps. So let's look at the graph. That has an intercept of -1, a slope of 2, so it's rise 2, run 1, and there is my graph right there. Now, what does that graph mean? What is that blue line? What do those points on the blue line actually mean? Now, when we first started chapter 3, we talked about that. The line represents all solutions to the equation, so it's all points that make that equation true. If the point is blue, if it's on the blue line, it makes the equation true, and if it's not blue, if it's somewhere else off of the line, then it makes the equation false. That's what the graph actually means. It's a collection of all points that make that equation true. So let's look at another one. If we have the graph of that guy, what does that graph mean? Well, again, we know how to graph it. We've done that over and over again. What it means is that any red point will make the second equation true. Any blue point will make the first equation true. Any red point will make the second equation true. Okay, what if we want a point so that both of the equations are true? Where would we find that? Not too hard to see, I hope. It's where the lines cross. It's the point of intersection. It's that green point right there. How can we check to make sure that's really the right point? Because maybe we didn't graph very carefully. Okay, we plug it into both equations. So that point right there is the point -1, -3. If I plug it into the top equation, I put -3 in for y, put -1 in for x for that first equation, plug everything in, and I get -3 equals -2 minus 1. Well, that is true. So that means that green point is on the blue line. Okay, now that's not enough. I need to make sure it's on both lines. So I plug it into the second equation. So I have -3 equals 1 minus 4, which is true. So that means the green point is on the red line. So the top part means the green point's on the blue line, the bottom part means the green point is on the red line. Therefore, the green point is on both the red and the blue line. That's the point of intersection. That's where both equations are true. Why do we have to check it in both equations? Well, it has to be on both lines. It's not enough to check it in one. Checking it in one just tells me it is on that one line. I have to check it in both. So let's go on to another problem that doesn't have quite so many words on it. So to solve a system of equations, here's what we'll do. First of all, we'll get the equations in slope-intercept form. On the last slide, both of those equations already were in slope-intercept form. But we want to get them in slope-intercept form just because it makes them easy to graph. Next step, we want to just identify the slope and the y-intercept for each. Most of you probably won't write that down, but it's a good idea to. It just kind of helps make a track record of what you've been doing, and so that you can see if you make a mistake where it might have been. Next, we'll graph them, we'll see where they cross, and then we'll check it in both of the original equations, not the slope-intercept forms, but the original equations. You want to check in the original, because if you made a mistake going to your slope-intercept form, then if you're checking it in a mistaken equation, that really doesn't help you. Okay, so let's look at these two. Step 1. No, they're already in slope-intercept form. We had that part done for us. That's good. Step 2. Okay, that's not too hard. The slope for the first is 3. The y-intercept is 2. The slope for the second is 2. The y-intercept is 0. Graphing those, graph the intercept first, then up 3 over 1. Graph the intercept first, up 2 over 1. Now, do you see why it's important to graph carefully? That point of intersection is going to wiggle around a lot if you haven't been a really careful grapher. And that green point right there is where they cross. That looks like it's the point -2 for x, -4 for y. So again, just looking through our steps, the equations were already in slope-intercept form. I looked for the slope and the y-intercept so that I could graph them. That takes me to step 3. I found where they crossed for step 4. Now I just need to check it in both of the original equations. And my original equations are my slope-intercept form equations because that's how they were given to me, so that makes it easier. And plugging it into the first one, I get -4 is -6 plus 2. That works out great. Plugging into the second, -4 is equal to 2 times -2. Okay, I will let you go to the next video now to see a lot more examples.